Right, welcome Analytical Mechanics. I'm going to record another lecture for you here today. This should be the last lecture in Chapter 4. Chapter 4 is about particle motion. In later chapters we'll look at extended objects in motion. Last time we finished up the discussion of how to add air friction into a problem. We particularly were looking at it for projectile motion and air friction, but it could work with almost anything. You just add a frictional force in and then take that into account in your solution. Sometimes the solution can't be analytic, like in the Mickey Mantle home run problem there in Chapter 4, or the cannonball problem that you're working on, that you will be working on, sorry, for Chapter 4 homework set. But for today, the last major topic that I'll discuss in this Chapter 4, we're going to look at charged particles. Charged particle motion. Well, what influences charged particles to move? Of course gravity does, but we're going to shut gravity off. We've got the magic gravity switch and we're just going to turn it off for right now. And what else? Air friction. Turns out we don't discuss air friction, at least the textbook doesn't in this portion. What can put forces on charged particles are electric fields and magnetic fields. These are lecture notes that go along with what's in the mechanics book for this, but I go in a little deeper than this. I pull some things that I normally do when I teach Physics 321, the electricity and magnetism upper level course. So first thing I want to look at is what's called Lorentz force law. Imagine you've got a charged particle. Here that charged particle is. And that charged particle is in the midst of an electric field that may get stronger or weaker, change in directions, so forth. That electric field is also caused by some charges, but not by this charge. The charge doesn't put a force on itself, classically. And so there are other charges, maybe off over here, maybe off over here, that are creating that electric field, but the charge is in that electric field, and we'll find that there would be an electric force. A force due to the electric field, which is found pretty simply by taking Q times the vector of the electric field. So in this case, if the electric field is pointing that direction, the force would point in that direction if it was a positive charge. If it was a negative charge, then the force would actually point in the opposite direction of the electric field. Well, do some simple mechanics. This is MA equals QE. A is the second derivative position, so R double dot equals Q over M times E. Q over M is an important concept. It's called the charge to mass ratio. When you take modern physics, one of the labs that you do is measure the charge to mass ratio for electrons. This then, of course, is three components, and so the x component of acceleration goes with the x component of the E field, but what determines the x component of the E field? Well, it's a field. Okay? So that means it might be a function of where you evaluate the field and at what time you evaluate the field. That function could be very complicated, it could be very simple. If the electric field were constant, then this would say we have a constant acceleration, and you know how to do constant acceleration problems. We did that earlier in Chapter 4, where we looked at acceleration in 1D or projectile motion in 2D, but only one direction of acceleration, one dimension of acceleration. Now, this is an electricity and magnetism class, so I'll just quote some results instead of us deriving them. Because of the mathematical nature of the electric field, that means you can't make the electric field just be any old thing you want it to be. Because what you make up might not match with the real world physics. But real electric fields satisfy del cross E is always zero. The curl of the electric field is always zero. Because the curl of the electric field is always zero, then since Q is a constant, the curl of the electric forces are always zero, which means that the electric force has a potential energy. The electric force is a conservative force. It has a potential energy. Now, historically, the way this is usually done is, instead of dealing with the force, we deal with the E field. So that's identically zero. And we say that E has a potential, and that's the end of the word. It's not potential energy. E does not have a potential energy. E has a potential that's written as a capital V. So E is minus gradient of capital V. The electric force is minus the gradient of, well, how do I turn this into a force? I multiply by Q. And that means QV is the potential energy. Electric potential energy is the charge that you're studying times the potential. And that potential comes from the field. And where does the field come from? Other charge. So there are two charges involved. There are the charges that are creating the field, and there's the charge that's having a force on it due to the field. Well, that then, what would conservation of mechanical energy say? The kinetic energy plus the potential energy is a constant. Little v squared plus q times big V is that constant mechanical energy. So that's one way to deal with problems, is through conservation of energy. And when you take an E&M course, spend an enormous amount of that course here at Taylor, a lot of it, maybe a third of it, just in looking at how do you find this potential. What configuration of charge over here causes a certain potential? Wind up viewing in terms of potential more than we deal in terms of the electric field. Because potential is a scalar. Scalars are inherently simpler than vector fields usually. A nice vocabulary word. That potential is measured in volts. It's the voltage. Voltage is potential energy. Voltage is potential energy per unit charge. Take the potential energy divided by Q. Notice I didn't specify anything about the kinematics of charge Q. It just exists. If it exists, there is an electric force. And that electric force, of course, will cause an acceleration due to the electric force that we begin the program. But now let's say that charge has a velocity also. Let's say that charge has a velocity in a certain direction. It's got a magnitude, it's got a direction. That doesn't change anything that I've written so far. The electric force does not depend on the velocity of the charge. But if in this same region there happens to be a magnetic field, let's say that points like that, and maybe points this way, and maybe points that way, somewhere else. And how would that magnetic field get there? Similarly, how the electric field get their other charges. The magnetic field is caused by other magnets. We put a bunch of magnets over here, they'll make a magnetic field, and that moving charge will have a force on it due to that magnetic field. The magnetic force, you got a Q in it, just like the electric force does. Uncharged objects do not have magnetic force. The B field is there, just like the E field is here, but you see I left a gap up there. This does depend on velocity. And maybe you recall that equation from you is magnetic force on a charged particle is Q V cross B. The magnetic force doesn't change the magnitude of V. In other words, the magnetic force doesn't make a particle go faster or slower. Well, but it causes an acceleration. What kind of acceleration is there if you don't change the speed? Changing direction. The magnetic force will change the direction of that charged particle, not the speed of that charged particle. Well, how do I know that? Well, for example, let's look at the power due to the magnetic force. Power is force dotted into speed. So this power, let's say the power transferred to that charged particle. Power transfer, or energy transfer per unit time. So how many watts? A car engine delivers power to the automobile itself. So many watts, so many horsepower. So I'm looking at the power that the magnetic force gives to that charge. I wouldn't have to put those parentheses in there because you have to do the dot product. I'm sorry, you have to do the cross product first before you do the dot product. Let's see, there's a little idea called the scalar triple product. That's what this is. It's three things multiplied, so it's a triple product, and it has to be a scalar, because V cross V is a vector, vector dotted into vector, it's a scalar. Well, it's proven in a typical vector analysis course, maybe in math methods, maybe in Calc 3, that you can interchange the dot and the cross. I don't think I wrote it down actually, I just looked on my notes and said, oh yeah, you can do this. Maybe you can't interchange the dot and the cross. You can interchange the vectors. For example, A dot B cross C is the same as B dot A cross C is the same as C dot B cross A is the same as C dot A cross B, etc. Something to do with the triple product. So let's do that here. So my magnetic force dotted into V, the power that the magnetic field is delivering to that charge, could be written as Q V cross V dot B. All right, interchange those two. Well, what's V cross V? Anytime you cross a vector into itself, you get 0. And that means no power is delivered to that object. No kinetic energy is added or subtracted. No speed change. The magnetic force doesn't change the speed of that charge, but it does change its direction. Just as a side note, since maybe you haven't talked about magnetism for a while, what do you measure B field in? Well, you measure it in newtons per coulomb meter per second. And those things are called Tesla. So a Tesla, that's the T for Tesla, not the T for kinetic energy. Tesla is 1 newton per 1 coulomb 1 meter per second. So if you have a charged particle with 1 coulomb of charge, and it has a speed of 1 meter per second, and it's moving in a 1 Tesla field, then there'll be a 1 Newton force on it. 1 coulomb, that's a lot of charge. 1 Newton, that's a small force. Turns out a Tesla has to be a really big unit. And we don't have very many magnets that make Teslas. Tesla is a large unit, as it turns out. And magnets that you'll find in the lab that you'll play with, refrigerator magnets, they're going to be in the neighborhood of a few thousandths of a Tesla, perhaps. All right. Well, we've got the force law now. So the net force, let's say the net force on my charged particle due to the electric force and due to the magnetic force is going to be Q times E plus B cross B. There's my net force. Now, if gravity was in the picture, we could also add gravity into that net force. If there was air friction, we could add air friction in that. But now let's just study magnetic and electric effects. So I want to look at various types of charged particle motion. Charged particle trajectories. Some various types of motion that charged particles can carry out depending on the E and B. Obviously, as in mechanics, you change E, you change the force, which means you change the acceleration, which means you change the velocity, which means you change the path. Or if you change B, you change the force, which means you change the velocity. Oh, but if you change the velocity, then you change that, and it's coupled together in a little more complicated way, perhaps, than you've seen. Okay. For our first one, something called cyclotron motion. And we discussed this in U-phase, and I'm just going to review what we do in U-phase with that and read up something else. Let's say I have a charge for the velocity. I don't know why I chose green, let's just hit green. And let's put it in the y direction. And we have a B field. X, Y, Z. Hang on a minute, I'm going to get a picture a little bit later. Make sure I get my graphics right. I want X to go into the board. match something that I do later on. Kind of a funky looking picture. From the top, it would look like X, Y, and then Z is into the board. So I've got V in the Y direction. So I'm changing this right in the middle as I'm talking about it because I want to make it match a later problem. I'm just going to cancel that and go over my extra notes. I don't want to get myself all miscombobulated here. You can always change the coordinate system as we need to. But I think I copied this from the EFIS notes, so I better just go with what I have here. So I have a charged particle with velocity v in the x direction. And we have a magnetic field that points strictly in the z direction. And we'll say there's no electric field at all. So we've got a region of constant, well, it's uniform and it's constant. The magnetic field doesn't depend on where you are, and it doesn't depend on what time it is. So it's a uniform, constant B field. So now my coordinates would be what? This is x, this is y, and z is going to be out at me. So my B field, remember this notation? B field that is coming out at you, looks like little arrow tips, so we have points with little circles. If it's going away from you, we put a cross in that circle. So x cross y equals z. So there's my magnetic field in the z direction, and I'm going to shoot a particle in the x direction. Maybe somehow we've got a magic boundary to our magnetic field that only exists there. There comes my particle. Well, that particle gets in here a little ways. Actually, wouldn't get in any distance at all. Well, let's pretend it's in there a little ways. And what direction will the magnetic force be on it? V is that way, Z is that way. V cross Z. Z is this way, sorry. V cross Z. V cross Z. It's going to be a downward force. Well, this is a horizontal velocity. What happens to a horizontal velocity when you put a downward force on that motion? Does it stop going horizontal? No. It just adds some downward with it. So that particle is going to start to curve off like that. Might look a little bit like gravity. Throw something horizontal, there's a downward force. It's going to be like a projectile. So the force at that instant would have been down. But now, the particle has moved. It's over here. Now let's do our V cross V again. The way cross product works is that the resultant has to be perpendicular to V and B. F is perpendicular. So I need something that's perpendicular to this way and something that's perpendicular to that way. If you do your right-hand rule, V crossed into B, you'll find that that force which, now just think about that, shoot something that way, but it's got a force at a right angle. What's going to happen in motion? It's going to make a curve. And of course, this is an instantaneous change. I'm showing it as if it's discrete, like it moves a little while, and then we look at the force. But this is happening instantaneously, and we'll find that that force just keeps pushing perpendicular to that velocity all the time, which is going to make the object move in a circle, or in this case, a semicircle. Now, if somehow we were clever enough that when the particle reached there, we were able to add in another region of magnetic field of the same strength out here, then what we find is that particle would just continue to do this, and it would move in a circle. Another way to make that happen is shut your magnetic field off, shoot your particle in, and when it's out here in the middle, flip the switch and turn the magnetic field on. That particle would start out going this way and then turn into a circle. It will circle around the B field line. Now let's double check our right-hand rule. If V is that way and B is out, V cross B, that's definitely down. So yeah. But right here, V crossed into B, that's definitely up. Yes. So my right-hand rule is working there. So this particle will circulate. Okay. This is assuming Q is positive. What if Q were negative? Well, that changes the sign of Q, which changes the sign of the force. So if I had a negative particle that I was able to shoot in and then turn the B field on, it would circulate in the opposite direction. The negative charge. This is called cyclotron motion. Cyclotron was one of the original atom smashers, in which they were able to affect the motion of charged particles. Not speed them up, not slow them down, but affect the motion of charged particles. And it turns out they could measure some of their kinematical and dynamic properties, mechanical properties, based on that circle. Circular motion, perhaps you remember from euphys. A force that causes circular motion is called a centripetal force. The acceleration is called centripetal acceleration. It doesn't change speed. What it does is cause an object to move in a circle. It looks like that. mv squared over r. But V and B are perpendicular, so if this is the net force, if the only force on the object is magnetic and it causes centripetal motion, and this is Q times V times B, so mv squared over r is QVE, cancel out a V, and V over R equals QB. The cyclotron equation that relates the 5 quantities: the mass, the speed, the radius of the circle in which it's moving, so that would be R, radius of the circle in which it's moving, the charge of the particle, and the B field. So measure 4, you can determine the 5th. Sometimes this is written, m times v is momentum. Turns out in quantum mechanics, momentum is more important than mass or velocity by itself, so you can measure momentum. This way, if you know Q, B, and R, you can measure the momentum of the particle. V over R is sometimes called the angular velocity, or 2 times pi times the frequency, or 2 pi over the period of that circular motion, and that's going to be QB over M. So if the mass of the particle is bigger, the frequency is smaller, which means it doesn't go around as fast, as often. If Q is big, that means a bigger force, that means a higher frequency. If the magnetic field changes, so forth. So there are lots of little relationships between the that. And this is an important relationship for use in particle physics, where you shoot charged particles into magnetic fields. You've probably seen some of those pictures. And a particle comes in moving incredibly fast. If V is super big, What's the radius? Radius is m v over qv. If v is really big, what's the radius? It's really big. And what does the radius of really big look like? It's basically going to go straight. So you see these pictures with lots of particles coming in, moving basically straight, but then they collide with something else, and bits and pieces go flying everywhere at various speeds, always slower than this, and so then they start to make circles, and you can determine from measuring the properties of the circles, you can maybe figure out what parts were there. I've heard it described as a little bit like taking two cars and making them have a head-on collision at 150 miles an hour, and then you go out and pick up the pieces and figure out what the cars were. You find a chunk of a piston here and a little bit of a valve there and a bit of a tie rod and part of an axle, and from that you reconstruct what the cars were. That kind of idea. A fun little analogy right here. Okay, that's cyclotron motion, a simple type of magnetic motion. The mass spectrometer deals with this. The mass spectrometers are much more sophisticated nowadays. I talked to Dr. King about the chemistry some about them. That was his area of expertise in graduate school, was mass spectrometry. But at least the basic idea that the mass spec is built on is that you've got a region of magnetic field and you shoot ions at it. Maybe an ion, maybe what you know is that it's an atom and you ripped off one electron from it. How do you rip off one electron from an atom? Well, I'll let you talk to the chemistry people about how they do that. But let's say we've got an ion with a charge of +1 times the electron, and it's got some speed. So I know Q, I know V, I know B. This particle goes in, makes a circle, the radius 2r. You know Q, you know V, you know B, you know R. What can you solve for with that? M. And you can find the mass of that particle. Mass spectrometry. Well, let's say you're shooting a whole bunch of ions of different masses, and then you get a bunch of different semicircles out of this. And by measuring the different radii, you can determine the different masses. This is how isotopes were often initially discovered. If you have a sample of carbon, well, you've got some carbon 12 and some carbon 14 and some carbon 15. Chemically, they're all the same.